going to talk about GraalVM and its impact on the Clojure ecosystem as we know it. Let's start with a bit of background. When we have a language on top of JVM, Java, Clojure, Scala, we typically start by some form of ahead-of-time compilation, where we process the language by a tool called Java C, Scala C, or the Clojure core compile function, and we get some form of JVM bytecode. It might be persisted on disk as a class file, or it might be just stored in memory if we never bother to persist the classes we generated in our Clojure repo. And then the JVM kicks in, takes those files, and starts executing them slowly, very slowly, using an interpreter. And then when the JVM figures out that particular functions, particular methods are executed over and over again, it begins the process of just-in-time compilation, which translates those particularly expensive methods into native code, into native representation. And this native code for our machine, be it AMD64, ARM, you name it, is the target representation, which is then executed on our CPU. Not all of the code is just-in-time compiled, only parts which are expensive from the perspective of the JVM. And both of those compilation stages are very interesting, but in this talk I'd like to focus on the just-in-time compilation. The way it looks on the JVM landscape has evolved a lot, and it began in 1999. Hotspot, the original compiler, the original just-in-time compiler, which is 20 years old now. And it's a marvelous piece of engineering. It's a massive project implemented in C++ and assembly, which does exactly the trick of getting JVM bytecode as input and then generating faster and faster native code as output. We're talking about a nearly 20 years old C++ project, which to the best of my knowledge 20 years ago was 250,000 lines of code. I guess it hasn't shrunk since then. Technical debt and all the cost of maintaining such a massive code base, well, are to overestimate, right? We are seeing that newer and newer versions of the JVM bring less and less impressive optimizations, less improvement speeds over time, right? Each extra improvement optimization comes at a higher and higher cost. And authors of JVM came to the conclusion it's time for a fresh start. It's time to change something. Maintaining this massive code base is not going to scale, especially as our expectations, our needs change over time. The way we wrote Java 10 years ago is not what Java write these days, right? We say do more functional stuff. We use more immutable objects. Then we generate bytecode from Scala or Clojure, and our bytecode looks yet differently, right? We have to adapt, and Hotspot just can't adapt anymore. JVM enhancement proposal 243 introduced the JVM compiler interface shipped in JDK 9. This is an interesting interface which allows authors of JVM to plug in their own just-in-time compiler written in Java. The interface in question, I'm oversimplifying, but it boils down to pass a method in JVM bytecode as an input, and as an output expect optimized machine code, right? An interface defining a just-in-time compiler. I'm oversimplifying, but that's a rough idea. And now with this in place, authors of JVM don't need to, if they want to change something, they don't need to change this massive C++ malloc. Instead, they can modify the greenfield new JVM Java new compiler implemented in Java. And the compiler in question is called Graal. This is a project which started a couple of years ago at Oracle, and this is the compiler interfacing with this JVM CI, this compiler interface, in order to offer optimizations in question. The thing has been released as GraalVM 1.0RC1 in April, more or less. You can read more and get all the marketing from the main website. The first time it appeared on my radar was shortly thereafter, when a colleague of mine wrote an interesting blog post in which he used one of the components of GraalVM, called the substrate VM, we will get there, in order to compile a simple Java web application into a tiny native binary and then into a tiny Docker container. I found it fascinating and I thought, well, this might work for Clojure. And shortly thereafter, after 3 days later, I published another blog post which took all of his ideas and translated them to Clojure. So this is my path. Since then, I experimented a bit with the technology, was trying out various bits and pieces, how we can combine existing Clojure tools with this head of the compilation. And here I am right now, sharing what I've learned since then. Let's move on to the architecture of the entire system. In architecture, one of the most important things are the actual groups, actual stakeholders interacting with the system. And in this case, I think we can identify 3 main groups of stakeholders interacting with GraalVM. First of all, JVM engineers, people who work on this compiler, improve it, add new target platforms, add new source languages, adapt the just-in-time compiler for new ways we use JVM-based languages. Second group are authors of languages. GraalVM, as I'm going to show in a second, offers an excellent platform to try out ideas. If you have an idea of a programming language or an existing programming language which lacks an implementation, you can take Graal tools and implement your language on top of them, getting all the benefits of optimization, garbage collection, other things coming with JVM. And finally, the group which I think is most relevant to this event are programmers and end users of this application, which are getting better, or at least completely new tooling to work on JVM, and end users who will get a faster, will get an environment able to execute all those applications faster. And with those groups in mind, let's take a look at all the pieces of GraalVM. I already mentioned a couple of different words and acronyms. Let's put them all in place. We've got our JVM, but without hotspot, without this just-in-time compiler we mentioned, with the existing one. And then over JVM CI, Graal, a normal Java library, which happens to be the compiler, communicates with JVM and responds to requests to pre-compile or to just-in-time compile a method. And this is the level at which JVM engineers work, right? They have a completely new tool to experiment with their ideas, to try new things. Those pieces are independent from each other, right? With this, the JVM itself stays pretty much the way it used to be, but Graal jar files can be just swapped in and out. You just start JVM with a different just-in-time compiler without the need to recompile your entire project. So you will need to recompile your entire virtual machine. This out of the box supports things we can compile to JVM bytecode. Java, Scala, Kotlin, Clojure, and anything else which we can curse to produce class files and orders. Now, not all of us, when implementing any programming language, want to go that low level and start emitting their own JVM bytecode, right? There are tools for that, but it requires a lot of expertise. So there comes another interesting abstraction, in between layer called truffle. Truffle is a set of APIs, a set of tools acting as an intermediate representation. Using truffle, you don't need to emit bytecode, you don't need to directly integrate with Graal as a language creator, language implementer. You are targeting the truffle layer, specifically implementing your language in terms of an abstract syntax tree primitives exposed by truffle. You're essentially writing normal Java, translating your language into tree of nodes with various, which corresponds to various operations of your language, which are then executed in an abstract way against traffic. And then GraalVM uses your representation to translate your language to the Graal level, and then benefit from all the optimizations and benefits making your language run on JVM shipped with Graal. An example of using truffle in practice is Truffle Ruby. Truffle Ruby is a project which is a couple of years old now and is a state-of-the-art Ruby implementation, which implements those truffle APIs in terms of, or rather implements Ruby in terms of those truffle APIs. Truffle Ruby is by far the fastest Ruby implementation out there. It outcompetes old JRuby. I mean, JRuby, traditional JRuby, in most benchmarks. And it's a completely different story when you compare it. However, the difference is even more pronounced when you compare it with traditional Ruby implementations, like the Max Ruby implementation, or traditional canonical implementation. I'm saying when compared to all the traditional JRuby, because since then I think all of it or a lot of truffle was merged into JRuby, and if you now run JRuby on top of JVM with Graal enabled, it automatically switches to this thing and everything is blazing fast. I think, but I haven't tried. But that's what I read. It's fascinating. It's a complete game changer, and also a proof that this platform scales not only to languages we consider static, like Java, but also ones which are highly dynamic, like Ruby. Another interesting thing is called Sulong. Sulong is another thing on top of truffle, which implements LLVM bytecode in terms of truffle. In other words, if you have a language which you can compile to LLVM bytecode, C, C++, Rust, you name it, there is a lot of languages which were implemented in terms of LLVM. You can then execute your LLVM bytecode on Sulong, meaning on Graal, on truffle, meaning on Graal, meaning on JVM. So you have Rust project compiled to LLVM running natively on JVM. One of the main reasons why alternative implementations of Ruby were incomplete, the most pronounced pain points of alternative Ruby implementation was the C API. The actual low-level API allowing you to directly operate on various Ruby objects. It was difficult to get right. It exposed too many internal nitty-gritty details. What those people did, I mean, authors of Truffle Ruby, they just took your C extensions written for Ruby, compiled them using Sulong to LLVM bytecode, and then let them run in the same virtual machine along Ruby, along Truffle, which is brilliant. And there's more. One of the main authors, one of the main goals, or one of the at least very important goals for Graal, was to be completely language agnostic and allow language interop. and completely polyglot environment for interacting between various languages in the same process, in the same virtual machine. To the degree that when you say you're running Java and JavaScript in a single Graal virtual machine, your calls from Java to JavaScript, from the perspective of Graal, those languages disappear, right? It's just bytecode calling bytecode. Optimizations inlining spans languages, right? Your JavaScript functions will be inlined into your Java methods. And same here, right? C extensions will be inlined into your Ruby code at runtime. So it's quite fascinating. Okay. So we have those three main target groups, right? JV engineers, very happy. They are working on a Java project with all the safety net of garbage collector and other guarantees. Authors of languages can use Truffle to demonstrate that Ruby can be done quickly. But how do we benefit from the I believe that there are not that many language implementers among us, and if there are, try it and let me know. Let's talk about the last group, right? What are the benefits for the last group? We have this new polyglot VM, right? We can call languages however we like in any combination, and we have impressive tooling which covers a lot of interesting use cases we might have not previously thought of. For example, using debuggers, profilers, heap analyzers for language X to look at language Y, because those languages disappear at runtime, right? They're like all running on the same platform, so all the tooling still, and so all the tooling for one language blends itself and works well on another language. Another thing is faster execution, right? There have been reports from Twitter, for example. They were running GraalVM earlier versions, way before first release candidates of 1.0. They were running some of their services written in Scala using GraalVM, and I forget the actual numbers, but they were very happy with the results and general stability of the pattern. I don't want to go too deep into this particular topic because it depends on your individual mileage, right? Every one of us maintains different projects under different load. Your results may vary. Check it out and see how those optimizations affect your particular projects. But the third thing, which I think is, from our perspective, the most interesting one, is native compilation. One of the tools which came together, which comes in the package when you download GraalVM, is a utility called native image, based on a tool which corresponds to the tool called substrate VM, allowing us to take pre-compiled JVM bytecode, essentially a fat jar, or as we call it, Uber jar, and translate it into a native pre-compiled binary for Linux or Mac. I think support for Windows is coming. And I think from our perspective, this is the most interesting value proposition. Okay, so I've heard this at Clojure meetup, and I haven't forgotten about this. Finally, let's talk Clojure. Clojure has problems. And some of them are quite serious. Let's take a look. In the latest state of Clojure, we saw some we saw voice of the community, right? There are naturally the notorious error messages. Luckily, that's something which Alex Miller and the team are already working on. We see some improvement based on Clojure's stack coming in 1.10. It's something which, well, at least is being addressed. Another thing, hiring and staffing. No surprise, right? There are no seniors. We have to hire younger people, train them, and turn them into seniors. no more need more docs tutorials. There are interesting attempts to create better documentation utilities online. A Clojure CLJ doc.xyz is a very interesting new project by Martin Klepsch in Berlin. But notice that none of those things on the top prevent us from introducing Clojure in a particular environment, in a particular platform, apart from this one, scripting difficulties, right? That's something which many of you might have run into. The fact that if we want to script something small in Clojure, we either have to drag an entire JVM with us and pay for the time for the whole thing to initialize, or rely on some other projects, some of them brilliant, for example, Lumo, right? This tool which allows very efficient invocation, very efficient execution of Clojure scripts based using, oh, I forgot the name of the engine, JavaScript 1, I think is the name of the JavaScript engine used in Lumo. Correct me if I'm wrong, I forgot. Anyway, Lumo is fascinating, try it out. It allows us to script in Clojure script and have it execute very quickly on top of Node. On top of Node or on top of another JVM. But it still takes a while to spin up the virtual machine, to load all the code, compile it. And whenever there is a virtual machine, we have to pay extra cost for either slow execution or having just-in-time compiler built into this VM, into this platform, and all related costs, such as the entire extra memory spent to maintain the state of the just-in-time compiler, to maintain all the compiler infrastructure in place which we need at runtime. And what I think is a massive differentiator which GraalVM offers is the ability to precompile Clojure to native binaries using Substrate VM and native image. Okay, now we can see some code now. We download GraalVM Community Edition 1.0 RC5 from GitHub. It's one small download coming with a lot of interesting tools inside. What you get in the package is not only an entire JVM based on top of Graal, but also an environment for running JavaScript, R, and Sulong, so LLVM support. When you unpack it, you look into the bin directory and you run into binaries called Java, Java-C, Node, and they're exactly what you think they are, but based on top of Graal. Let's try it out, shall we? We will write a handful of Clojure. And what we see here is we read stuff from the standard input. Then we read all the values we passed as arguments, and then we make a nested lookup into the data structure. In the data structure we read from standard input, and then we quickly print the result. A fairly small command line utility in Clojure. We can use Leiningen or your favorite tool to compile it to an jar, a precompiled jar file. And when we run it using good old traditional Java, passing that hash map with a vector inside and saying look up keyword A and then the element at offset 1, it prints 3 and tells us a tiny bit about how long it took, right? It took 1.5 seconds of wall clock time, and it needed 112 megs of RAM. We can play around. JVM gives us a lot of parameters which we can tilt and operate to modify the behavior of the JVM. And for example, if we pass this option, which tells Hotspot to stop compiling, or rather stop further optimizations after a certain point, we can win both a bit of memory and a bit of time at the cost of slower top speed execution. Just quite nice, right? JVM gives us a lot of flexibility. let's take a look at what Substrate VM can bring to this tiny project. Using native image we got in our package from GitHub, we can pass a couple of options to it. The most important being the actual name of the jar file we want to compile, and one other interesting option being report unsupported elements at runtime, saying if you run into something which isn't supported by the ahead of time compiler, don't worry, just put an exception throwing code there instead and carry on. Otherwise, native image might complain and print a less than intuitive exception. This turns it into a runtime exception, which will show you the same stack trace, but chances are you will never see it because the actual code path you are following in your pprint jar program never hits that path. It takes a while, and like 4 gigs of RAM, but it happened only once. And then we end up with this small library called pprint, and when we run it again, the situation changes. And the situation changes a lot. And this is fascinating, right? You just keep experimenting with various tools, various small command line utilities, and it just keeps falling to such tiny numbers. The reason why this is so powerful, especially in case of Clojure, is the fact that Clojure does a lot of initialization, initial bookkeeping, in those static initializer blocks. You might have seen the static initializers blocks in Java. That's what Clojure uses to initialize a lot of stuff. Native image aggressively tries to initialize as much of it as possible ahead of time and just store pre-computed values in your binary. As a result, the binary is like 17 megabytes big, but at start time, there are very few things left to initialize. We do pay the cost, I have to admit, we do pay the cost of lower top speed. A warmed up JVM will execute the code faster than our pre-compiled binary, but I mean, it's software, trade-offs everywhere. Okay, we can build nice, small, self-contained binaries using this tool. What else we can do? Well, we can build a web app. Let's implement a simple application which acts as a dictionary, key value storage. I can put a value under key city and then I can get this value. That's the entire API I want. I will store those keys in my temp directory. To implement this API, I need like this much of Clojure. I don't expect you to read it, it's too small, but I'm just saying this is not a lot of code. Interesting libraries I'm using is HTTP-Kit as my server. Ring middleware to do all the parameters, parsing, and such tasks, and finally BIDI for routing, just a handful of libraries. This thing, when translated into an Uber jar and then compiled using native image, results in a nice self-contained library, which does exactly what's written here, and exposes the interface I specified on the slide before. Now, instead of looking at its memory usage and stuff, let's take a look at a different thing we do often. Let's ship it. Let's ship it as a Docker image. What do we need to do? Well, let's see. Let's start with Ubuntu. We will get lining and curl and a couple of other things we need for ahead of time compilation using Graal. Then we will download Graal from the GitHub link you can find online, untar it in the opt directory. We will add project CLJ, get all dependencies, then add all the sources, compile them, and prepare our native image. An invocation very similar to what you saw 5 minutes ago. Right, and we end up with a corresponding web key value, web key value.main binary. And then the twist, we start from scratch again. We start from a completely empty base image, which consists of nothing. We copy our binary from the previous image, put it in the root, and we say then when the image is started, execute the binary there. This binary, thanks to -- static, is self-contained. It has all the dependencies statically linked in. It has no dependencies. And the resulting Docker file is 13 megabytes heavy. To put it in context, the smallest JVM I was able to find on Docker Hub was 70 megs. Right? We are in the ballpark of Go, right? Which also is able to produce such small native images. Of course, Go's application will certainly be much faster because their compiler is years of experience and optimization for such workloads. It will be slower, but it's a proof of concept, right? It's demonstrated that the thing is possible. And Clojure, highly dynamic language, can be turned into such a tiny binary. I'm not done yet. Let's switch our attention to command line utilities. I like Unix. I like operating on simple programs which do one thing, do it well, and pipe the results back and forth between inputs and outputs. One program you can write. Credit goes to Taylor Wood, who came up with the idea in May. We can write a simple utility called JSON to Eden, which takes JSON stream of JSON inputs and produces a stream of corresponding Eden outputs. It operates on an endless stream. Right? We repeatedly read something from the input, parsing all keys as keywords. And when we run out of the feed, we return a namespace keyword end of file, and we keep consuming until it's end of file, and then we print one after another. Right? When we say pipe a package JSON file from our favorite Node project, we end up with the following Eden soup. No surprises here, right? It's fast and tiny. I mean, by fast, I mean it initializes very quickly. What can we do with such an Eden soup? One fascinating project I ran into not long ago is called Spec Provider. Spec Provider is based on F# type providers. You feed it with a lot of Clojure values, data structures, and it tries to deduce a Clojure spec specification corresponding or matching all of those values. I like it a lot. The way it looks is you require spec providers as SP, then you have a handful of values. You infer specification of all of those values, and then you can print it. And it says that, well, based on what it saw, small map has following required on namespaced keywords. C is either a keyword or a string, B is a string, A is an integer. Right? It's brilliant. I stole this example directly from the readme of the project. So what we can do now, well, we can wrap it in a nice Unix command line utility. Same story, right? We have a main function which takes a name of the specification we want to deduce, and then we keep reading elements, generate a lazy sequence of parsed values from the input, and then we infer specs of all of those inputs. Then, using keyprint specs, exactly like on the last slide, we print all those specs with the keywords passed as the input to the function, saying that we promise to alias to require Clojure spec with alias s. Before we run it, let's add another tool. It's called zprint. It's a pretty printer. It's a code formatter. It uses it might be the project with the longest README I have seen on GitHub. Going through all these rules, how like we can customize the format, the style of the produced code. And the cool thing is, I didn't have to do anything because it comes with native image precompiled binaries for Mac and Linux with every release, right? So I just downloaded one of those, and then I just created a tiny Unix pipe. I got a handful of packaged JSON files, translated JSON to Eden, ran spec provider on them, and pretty printed the result. I got a whole lot of output, and last lines look like this. 0.3 of a second of wall clock time, and 100 megabytes for the entire pipeline, right? All tools running concurrently in a single process group. It's not super fast, right? Like, I mean, a couple of files and nearly half a second of runtime. It's not fast, but I really like the fact that they can start building, can begin to use Clojure to build such simple command line utilities, right? When I talk with customers about Clojure, they ask me from time to time, okay, the language looks okay, a JVM, nice platform and everything, we can use all of our old Java code, cool, but let's switch gears and tell us what's a situation, a context you would not use Clojure in. And I say, I don't know, when I need to write something which starts quickly, this changes the situation, the landscape entirely. Before we get too excited, let's talk about limitations. There are some, and interestingly enough, authors are super transparent. They have a file called limitations.md, and they specify one after another. They keep the list up to date. A lot of those things are mostly supported. A lot of them are unsupported, but on the to-do list. Some are impossible to pull off. For example, dynamically loading bytecode at runtime. There is no JVM left, so where would you load the bytecode? In the Clojure world, dynamic class loading is something which keeps happening and happening in the development environment, right? When we are tightly integrated with REPL and just keep working in tight feedback loops, pulling new versions for namespaces, compiling them, seeing how they work on our old data. We do it all the time, but do we do it in production? Less often. Sure, sometimes it's nice to connect to a running JVM and inspected state over the NREPL protocol, but it's not a big sacrifice to say, okay, we don't need it, we can just precompile the whole thing to a nice small native binary. Another thing which might be a problem are reflections. Luckily, we can instruct Clojure to tell us when reflective calls are happening. But to be honest, Clojure is surprisingly static after it has been compiled to JVM bytecode. When you compare it, for example, with Java, modern Spring Boot applications, with all the annotations going on at startup of your Java web app, a lot of bytecode generation occurs at runtime. In comparison, Clojure appears to be surprisingly static. Thus, this limitation might be less relevant to us. Time will tell, experience will tell us whether it's true or not. There are some open questions I need answered. First one is serverless. That is, how can I use those native libraries as some form of function as a service? Will I need to use it statically linked applications, or will I precompile my JVM bytecode not to an executable, but to a shared library? And then I will link with the shared library from my Node process or Python process running in, say, AWS Lambda. Might work, it might not. I need to check it out. Another thing is encryption, TLS. I'm not exactly sure whether I ran into some problems I wasn't able to solve myself, and I forgot to read something in the README, but I wasn't able to communicate with other services speaking TLS. For example, HTTPS. I could have accessed things over HTTP, but when encryption kicked in, suddenly GraalVM, Substrate VM built. Binaries told me, no, not implemented, boom, and crash. Maybe they're working on it. I still have to read more about this. Okay. We've covered a lot of ground today. We discussed roles of a role of a typical ahead of time and just-in-time compiler, focused on just-in-time compilation, and looked at the state of the art, how Hotspot helps us to run our code faster, independently of the source language we're writing applications in. Then we looked at problems of such an old, large code base written in a language which is more challenging to maintain in the long term. And then we fill this gap with GraalVM, which has benefits for a whole, which offers benefits to a number of stakeholder groups. But for us, Clojure developers, the most interesting might be this native ahead of time compilation, which drastically broadens the landscape we can use Clojure. I encourage you to download the thing, give it a try, play around, see it break, see it work. Oracle folks maintaining it are keeping all their issues on GitHub. They are very responsive. They appear to be very nice, communicative people. So give it a go, and yeah, let me know if you like it. This is all I've got. You've been a wonderful audience. Thank you very much.